first off, there is an equation that relates the velocity, the frequency, and so in terms of this equation, V is the velocity, F is the frequency, and then lambda would be the wavelength. So then, given something like this, so if V is 344 meters per second, the wavelength is 2.5 meters, what would be the frequency?
Plug into the toy.
Plug into the toy. Now the question is, can you plug it into the toy and get the right number? Anybody?
Isn't there a way just to just rearrange it so you can?
Yes, you can.
Can you just divide
So that's
V by
7,
Yeah,
6.
exactly.
F equals V divided by
Right.
lambda.
Again, any of these equations that we talk about throughout the quarter, you ought to be able to take that equation and solve it for any variable, right? Okay. So in this case, I gave you the velocity, I gave you the wavelength, I want to know the frequency. So yeah, so basically I need to take this equation and solve it for F. And so F would be V over lambda.
137.6.
And you end up at 137.6 what? Hertz. Right? Again, the numbers will have with them units, right? It's not just a number. So the frequency is going to be 344 divided by 2.5, and we end up at 137.6. Let's go. Next week there will be a test. Okay. Okay. The test basically all have the same format in that the first part is basically just terms, so short answer type stuff. Okay. The second part, the more fun part, deals with doing this kind of stuff. The math part.
How often are they going to do tests?
For you, every 10 minutes.
Sure. Yikes.
It's in the schedule, and it's always,
Okay.
yeah, like every couple weeks.
Every moment of my life is a test.
Okay.
That's right.
All right.
So, if you were trying to find the wavelength, would it be wavelength equals F over V or V over F?
V over F.
You should just move out the U. So.
Right. Yeah. Again, the way you solve an algebraic equation is you always do the opposite operation. Okay. All right. All right. So, in terms of a wave, if we're talking about a wave in a solid material, we can also find the velocity of that wave. And so V will be given by the square root of E over rho. Right. So in this equation, E is Young's modulus, which is a constant. In there you can find tables of these sorts of things that's dependent upon the material. Okay. And rho is also dependent upon the material because this is the density of the material. And again, that's a constant.
If this is referring to waves in a solid material,
Right.
what was the previous one referring to? Just
Right.
like
Okay.
moving through air?
Right, through air. Okay. So, for example, let's say I want to know in terms of what is the velocity in steel. Okay. So, in terms of for steel, then you got that E, Young's modulus, is 19.5 times 10 to the 10th per meter squared.
And that's always going to be the same?
Yes. Again, it's a constant for whatever, again, for the material. Okay? And then the density of steel is 7,700 kilograms per cubic meter.
And the representation is rho?
Yes.
Is that what that's what? Okay.
So what is that symbol again?
Rho, R-H-O.
R-H-O?
Yeah. Yeah.
It's kind of like a P with a...
Yeah, it's sort of a squib type P.
I've never seen it.
Right. So you would take those numbers and plug them into the toy and or the app. Okay. Again, the value of Young's modulus is given in terms of scientific notation. So hopefully on the toy or app, you have a key that allows you to do scientific notation. Okay.
Oh,
Right. And you plug that in to this, we get that the velocity V is going to be the square root of 19.5 times 10 to the 10th over 7,700. You plug that in, and you end up that the velocity of a wave in steel comes out to be 5,032 meters per second. Does everybody get that?
So just to ensure, make sure I'm on the same page, velocity is always expressed in meters per second,
Yes.
or at least with what we're doing.
Yes. So
The
generally,
densities are always expressed in kilograms per meter
Right.
cubed.
yes. Yeah, so generally in class we'll be doing things in terms of the units that are used in physics, which is in terms of metric.
Okay.
Okay? Yeah. So generally in science things are always done in metric units.
So I looked up rho.
You looked at that?
Yeah.
Okay.
Pretty cool. I didn't know Greek letter, it's pretty cool.
Okay. Did everybody get 5,032? You did? All right.
10 to the 10.
Yeah, and hopefully on your calculator and or app, you have the ability to do scientific notation. Because Young's modulus numbers are always going to be in terms of scientific notation because they're always fairly large numbers.
I forget, what's the U with the extra line that's kind of like a P and a U mix?
P and the U mix.
Yeah, it's like a. It's like
You about on page 41
yes.
at the bottom?
Yes.
Mu. M-U.
MU.
Okay.
Good man. Good man.
Right. 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 Any question on doing that calculation? We've got it into the toy, the app. Got it to work. Going. After all, next week. And in terms of all these examples of various problems we've been doing, you can expect that you'll probably see something similar to that on next week's test. Now, how about velocity of a wave in a wire?
Cool.
So the other side. So the velocity in the wire is given by the square root of t, where t is the tension of the wire. And then in terms of mu. Yes?
Would this be equivalent to velocity in a string?
Right. Yeah.
Okay,
String
so
wire, yeah.
Guitar string maybe?
Right.
Okay, cool.
Okay.
Nice.
So what does mu represent?
Right. Right. So mu itself,
Oh,
and
is the mass per unit of length.
right. So T is the tension. So let's put it up here. So T is the tension in the wire. And mu, it's almost similar to density in the last equation, because it is the mass per unit length. So basically it's similar to density. Right? And so mu itself is going to be given by that. Right? So it's going to be the mass per unit length, and you think about a guitar string. What is the shape of a guitar string? At the end.
Essentially, it's
You look at the cross-sectional area, what is it?
cylindrical.
It's a circle, right? And so what is the formula for the area of a circle?
2 pi r?
Nope.
Pi r squared?
Yes.
2
Okay?
pi r is what, that's the
So area of a circle is pi r squared. So that's basically why you have that in there. Okay? So rho is the density.
I'm sorry, I'm having trouble understanding what does that equation in the lower left have to do with?
Well, because that is what mu is.
Oh, okay, that's the.
Right?
Cool, thank you.
So eventually you got that in a question or in my question next week. Is okay, you have a steel wire where the diameter, right? So let's say we got a steel wire. The diameter is 2 millimeters. Oh, let's see. We want the tension in the wire. And let's say that the tension in the wire. Oh, let's do by density of steel, we had that up earlier,
5,032.
is 7,700.
My bad. I did velocity.
Heavy is tension should just be force. They should just be. All right. So I want to know what is given this equation, given these numbers. What would be my velocity? Okay. So first off, the diameter is 2 millimeters. Right? Well, if the diameter is 2 millimeters, what is the radius going to be? 1 millimeter, right? After all, the radius is half the diameter. All right? Millimeters is not in the right units. 1 millimeter is how many meters?
One millimeter?
It's how many meters?
It's 1,000th of a meter.
Right. Move it over 3 places. Right? So this is going to be 0.001 meter. Right? Okay. But again, you got to make sure everything's in the right units. Okay. Now we can take our numbers and we could plug them into our equation. So V equals the square root of, in this case I said 650, over rho, which is 7,700, times pi, times 0.001 squared. Right? So now everybody can be able to plug that into the toy. And or app, and come up with my velocity in this. And so to the nearest whole number, that comes out to be
Very small decimal?
nope.
No? Okay.
I got 0.000000265.
That would have been,
The thing is, right, but the thing is not moving in it, right?
Yeah, 52.
Like 51.8.
How much?
51.8.
Oh, now it's somewhat moving. Unlike the other one.
we're making progress.
We're making progress. It's actually going someplace, all right? Any other takers? So to the nearest whole number, 164. Yeah, we have a winner. my velocity will be on the order of 164 meters per second. There you go. All right.
Pretty straightforward. I think the hardest part is just punching in the calculator correctly.
Yes. Okay. All right. So again, in terms of this, parentheses are your friends. Again, if you've got more than one operation going on in the numerator and or denominator, you need to use parentheses in order to make it work. Okay? Now, depending on your calculators, like the graphing calculators and some of the TIs, once you hit square roots, it automatically gives you an open parenthesis to start with. So you hit square root, you get the open parenthesis, you type in 650, and then you go divide, then you go another open parenthesis, and then 7,700 times pi times 0.001 squared, close parenthesis, equals. And again, to the nearest whole number, you ought to be coming out on the order of 164 meters per second. Right? Right? Okay. So if I have a wave on a string, in this case traveling out in that direction, and at the other end it's fixed, okay? So this end is tied to a wall. What happens to the wave when it gets to the end?
I would say the energy is somehow transferred to the wall.
So what's going to happen to the wave itself?
It's going to dissipate.
It's going to bounce back, okay? And when it bounces back, is it going to be traveling on the same side or opposite side? Opposite, right? So the wave will bounce back. Okay. And when it does, point, it will now be traveling in the opposite side. Okay.
Is any, oh, go ahead.
No, you go ahead.
Well, my question was, just regarding the actual physics of it, is that there's going to be some of that wave energy that's transferred to the wall, right?
Right.
So it's going to be a smaller amount that goes back.
Yeah.
So let's say you had a string tied to two walls, like this, and then you plucked it and it continued. Eventually, would it keep going back and forth until there was no wave?
Well, then if you about a guitar string, once you pluck it, right after all, it's tied at both ends, right? Does it keep on going forever?
No.
No.
Okay. So it gets smaller every time.
Right. Yeah.
So there's got to be some energy that's being released somewhere
Yeah.
else. Okay.
Um,
Thanks.
So, it's showing me two pictures, like a free end and
Right.
a
Okay.
fixed end.
Right.
So,
So this is the fixed end. Belly is tied to a wall.
yeah.
If you do a free end, it just comes back on the same side. But But again, if you think in terms of guitars, violins, any string instrument, the way, you know, it's tied down, right? It's not just an open end, right, in terms of general. Right. Other properties they talk about in terms of waves, in terms of superposition and interference. Maybe. All right. So first off, superposition.
Wow.
What?
I mean, on a quantum physics field, that's being in two places
Well,
at
yeah.
once.
Well, we're not talking about
Okay.
but
There's got to be some relation, though. Since physics class.
it is a bit, right? But we won't get into the whole quantum part, right?
But it's not restored to two at once.
Right. So, for example, Casey and Drew want both of you to talk at the same time. Talk.
Oh, hey, Casey, how you been, buddy? I was at doing your escape plan.
All right. So, in terms of superposition, so for example, if I'm talking, Drew's talking, Casey's talking, everybody in the room is talking, you know, my voice, their voices, you know, they don't just cancel each other out, right? We're going to have to have multiple people talking all at the same time. None of the waves are going to annihilate the other waves and so on, right? Okay? In terms of superposition, right? It's the, you can have multiple things going on. Yeah. Okay? How go, you know, you think in terms of, you know, like opera singers, and you got several of them singing parts at the same time. You know, it's not that the one opera singer, you know, and the other one is going. You lose their voice and you can't hear them, right? Right. So that's superposition. Right?
Can they really break glass? I don't mean to jump so.
Well, you can.
I mean, it hasn't happened. Is that type of thing? I know it's super
It would be really difficult. Okay.
What, you didn't understand?
Right. But,
reaching a certain frequency.
yeah, supposedly, yeah, they reach the right frequency
Have
and
you
that
seen that
does
book?
volume strength.
I think I remember you showing us a commercial.
And I'm going to show you.
The Bud Light?
Yeah.
Awesome.
It is a great commercial. All right?
Yeah, it is.
All right. The other property then is interference. Okay? There are two types of interference we'll talk about. They're on opposite ends of each other. So the first type is constructive interference. So in constructive interference, we have our first wave going like this. We have our second wave going like this. So eventually it matches it. And so the net result here then is we end up with a new wave that has basically twice the amplitude. Right?
Like kind of additive.
Right, they add to each other, right? And so we end up with that. Okay. So that's constructive interference, right? And the other type then, on the total opposite end of the scale, would be destructive interference.
Wouldn't that be kind of like phase reversal or something like that?
Yes. So in destructive, again we have in terms of our waves, but this time they're going to be completely out of it. So now again, I have my first wave going like that. we have the second wave, which looks like that. So now here, the net effect is that they cancel, and you end up with the kind of thing you do not want to see on your EKG. Okay.
But then again, you wouldn't see it.
Oh, you're right. Again, you would not see that on your EKG, right?
Checked out somewhere.
True. Unless you're having like a super out of body experience where you're like floating above and you're
Sure,
like, fuck,
exactly.
I'm dead. Excuse my language.
Okay. So destructive interference, right? So you think in terms of things like noise canceling headphones,
Okay.
first off, okay? Or in terms of Boeing airplanes, make use of this.
Oh, like on the inside of it?
Yes.
It doesn't work towards the back of the airplane.
But again, so maybe, you have in the cabin of the airplanes, there basically are speakers that are there that generate noise that are out of phase with the engines in order to try to make the cabin of the airplane quieter. Otherwise, everybody would have to wear the same ear protection as those guys down on the tarmac for your flight, okay? Well, in terms of the speed of sound, so the speed of sound in air is dependent upon a variety of different things, right? So one of the things that it is dependent upon is the temperature of the air. Sorry, 331.3. So the temperature is the velocity is given by 331.3 plus 0.6 Tc, where Tc is the temperature in Celsius. Okay? So, for example, if the Celsius temperature is 20 degrees, what would be the speed of sound? Huh? Gotta have a toy for that, huh?
You said 20, right?
I said 20. You already said a nice number.
Is that 20? Okay, it's a degree. Okay.
That's a degree symbol.
I see.
343.3, right? Plug that in. So the velocity would be 331.3 plus 0.6 times 20, and you end up at 343.3 meters per second. Right?
6.1.
What?
343.1. And I was just being facetious, my bad.
No, because 20 times 0.6 is exactly 12.
But then how?
I don't know.
Oh, no, that's what they say, my fault.
Because 20 times 0.6 is a nice whole number. It's 12. Okay?
You're right.
That's what they pay me for.
Yeah, but I plugged in 0.1 instead of 0.3.
Okay.
All right, my bad.
All right, so now let's say on this particular day, there is a thunderstorm. And you do that usual thing of counting the seconds in between the lightning and the thunder. And you want to know how far away is the storm. Okay? So if on this particular day there is a 6-second gap, 6 seconds in between the two events, how many meters away is the storm?
You can use this if you wish.
So, to the nearest meter, how far away is the storm?
Wouldn't it just be
Distance is given to by the rate times time. So this is the rate. T is 6 seconds. So it's a matter of just simply multiplying.
2059.8?
So 2,060 meters, right?
Basically.
Yeah. Right.
So from this equation, it's saying that the hotter the temperature, the faster sound is in
Right.
the air, right? How does that make sense though? Because I thought air molecules were more condensed when it was cold.
So does it move slower when it's colder or faster?
Okay. So what does that say?
Slower. See, that's really cool. I never knew.
Yeah, because if it's 0 degrees, so if it's freezing outside, then it's going to be 331.3, right?
So it moves
Okay.
slower?
In it. Okay. So again, in terms of next week's test, after all, there will be a test next week. There will be a question like this where I say, okay, on this day of a thunderstorm, that the temperature is whatever, the time frame in between the thunder and the lightning is X amount of seconds. Tell me how far away is the storm?
So it would always be 331.3 and then the time times the temperature.
Plus 0.06 times the TC, yes.
So 331.3 is always.
Right, it's always, that's part of the equation, yes.
Is 0.6 always part of the equation?
Yes.
So you don't need to know the seconds. All you need to know is the temperature.
Okay. Well, again, the first part of my question on next week's quiz is you'll have to calculate this number. Okay. But now I tell you that the time frame between the thunder and the lightning is 6 seconds. How far away is the storm? Well, how far away the storm is the distance is going to be given by the velocity times the time. So you take the number you got here, multiply it by the time frame, and you get how far away is the storm.
Sorry, but how do you get 331.3 again?
It's part of the formula.
What does it represent?
It's really the base number here is based on the speed of sound at 0 degrees Celsius.
Okay.
You know, they could have done it in any number and then come up with an equation. Okay? But it's based on 0C.
I wonder if this has something to do, like I was just kind of brainstorming, but I think it's fascinating. The colder it is, the slower sound moves. Is that why in space sound really doesn't move, or does that have to do with only the vacuum?
Well, it has to do with the vacuum.
Okay.
Okay.
And no air molecules exist. Okay.
Also,
I'm just thinking
space is, you know, I think in terms of temperature,
It's hundreds of degrees.
it's on our scale, it's negative 457 degrees Fahrenheit.
Correct.
It's like a few degrees Kelvin.
Instantaneous.
Okay. All right.
Yeah.
Yeah, that's what I was.
They kind of form into a net, so you can see it as its connection, and then the hotter it is, like
Yeah.
all channels coupled up,
Right.
so.
Right.
Have you been watching the Cosmos?
Yes.
Isn't that amazing? I think it's incredible. I just love learning new stuff about that.
Okay. All right. So wait. Yes.
So for on the test, you're not gonna give us the velocity, are you? We have to figure it out for ourselves.
Right. So Bailey, my question will be similar to this. I'll give you a temperature. You tell me what is the speed of sound at that temperature, and then given this piece.
You just plug in the time then.
Yeah.
So it's always going to be 0.6.
Yes.
Okay, that's the constant.
Everybody uses their notes.
Right. Yes. Yeah. Quizzes. The tests are open book. They are open notes. They are not open neighbor. Okay. In terms of that.
Yeah, Mike, this is almost
Again, you got your notes. You got mine that are posted on the website under each week. Yes.
So we'd be able to use your notes as well, or?
Right. So waves. Right. So waves can actually move in all dimensions at once, right? So everything in terms of waves can move in 3 dimensions.
Would it be open book too? Your tests? Yeah.
What was the answer to that question?
I forget. I heard open note, but okay.
Yes.
All right.
Okay.
Cool, because I like this little thing right here with all the little.
All right. So waves can move in all directions at the same time. So I think in terms of me up here talking, the wave goes out in all 3 dimensions, right? So not just one. I think in terms of speakers, again, waves go out in all dimensions. Now, in terms of other various properties, you get to the Doppler effect. What is the Doppler effect?
I keep thinking whether.
It senses objects with frequencies that are in
Everybody's experienced the Doppler effect. The common thing about Doppler effect is you think that you, yes?
If you're gonna explain it, but the sound, like, the closer the object gets, the louder it is, and then once it passes you, then it dissipates.
So it has to do with not only how loud it is, it also has to do with the apparent frequency you hear, right? So again, the prime example is you're out in the street, you got the ambulance, fire truck, police car racing by you with the siren on, right? And there will be a change in the frequency from when it's approaching to when it's gone by you, okay? That is Doppler.
It gets higher when it's getting closer to your right and left as well.
Okay. So Doppler effect. And so really that occurs because in terms of sound, again, sound is 344 meters per second in terms of metric. And so basically if you think about the ambulance, fire truck, whatever, racing down the street. So let's say that that ambulance is going to pick up a guy who just had a major heart attack and that ambulance is only going 1 mile per hour. Are you going to notice anything in terms of the Doppler effect? No. Okay. So really, you have to be going a few percent of the speed in order to get it, right? How about Doppler effect with light?
Stroke.
Okay. Do we notice it on Earth?
That's a good
No.
question.
I wouldn't think so.
Because after all, what is the speed of light? The speed of light is 3 times 10 to the 8 meters per second, right? And again, in order to notice the Doppler effect, you have to be on the order of a few percent. Well, there's nothing on Earth that is anywhere as close to that, really. Unless you want to talk about the Large Hadron Collider. So,
Yeah.
But, okay? But there really isn't anything on Earth, as far as our everyday stuff, that we're anywhere near that kind of speed, okay? But there is a Doppler effect, by the way, okay? After all, that's one of the things that Hubble found and made use of in his work. and found out that the galaxies are racing apart.
Oh, that's how you developed the Big Bang Theory.
Yes.
Right, it's Big Bang, yeah.
Yeah.
Yeah. That was part of the evidence for the Big Bang Theory. Was that work he did? Okay. I don't know, that's the guy that the Hubble Space Telescope is named for. It's him. Okay. Right. I know the Big Bang Theory and that whole part actually was proposed by a Catholic priest. Okay. So a Catholic priest came up with the Big Bang.
It's funny what we forget. We would argue about later.
Okay.
But
You had a guy by the name of George Lemaitre,
definitely.
who was also a trained mathematician, but also a priest, who went through Einstein's math in terms of relativity, went through all the math part of it, and came down to the whole dense primeval atom and the explosion. Yes?
What is the lights version of the Doppler effect? Isn't
Red and blue shade.
Yeah, it's the red and blue. When it's red, it's going away, and blue is going
Right.
back.
That's what Hubble saw when he
Yeah.
looked.
Yeah, I was going to say, I thought it was something else besides
No.
sound.
Yeah. Yeah. So that's what Hubble saw when he looked. And found out that yes, there are other galaxies out there, and that they are moving away from us. Okay? Right. So Doppler effect. And let's bring this up here. So first off, if I have a sound source, okay, and it's stationary, then the waves are going to spread out equally in all directions, right?
That's a jet.
Yep, in this one, that's what they're using, right? And so, the spacing in all directions is the same, right? But now what happens if I give this object a velocity? Right?
The sound will be compressed.
And so if I go here, now I can give it a velocity. Okay, so basically the numbers up there are the relative velocity compared to the speed of sound. That's what those numbers represent. Okay. So now you notice that on the front edge of this, my waves are being compressed. Okay? And then behind it, the waves have a chance to spread out. Okay? So you think in terms of Doppler effect, that what's happening is that if you're in front of it, you got that all these waves are compressed together. So you hear the sound one way. When they go by, then it sounds differently in frequency, right? Well, then if you get to, in terms of now where I actually break the sound barrier.
Yes. I was going to ask, how does this?
Well, now what do you see in the front?
Nothing.
It's
Nothing.
overtaking.
It's passing it.
It's overtaking the
Okay.
waves.
Okay? Except for anywhere along that path, for the people who are on the ground, they get to hear a nice, big sonic boom.
So is compression what's causing the sonic boom?
Yeah, apparently the air cannot get out of the way fast enough.
Yeah, that's one of the
Right?
coolest things I've ever worked.
All right? So yeah, there's nothing coming off the front, right?
Right.
But everything's behind, and you get the sonic boom. So you think about a few years ago when Obama was in town,
Yeah.
and barely when the president is in the area, they have basically a no-fly zone, like a 10-mile radius. And you had that one old guy couple who came back home in their float plane
Didn't get the
and
memo.
didn't realize or know that the president was in town. And so they broke that 10-mile barrier.
Yeah.
And so they scrambled a couple of fighter jets out of Oregon.
Right over here.
And you heard the sonic boom here in Seattle as they came racing in. And this guy ended up with 2 fighter jets went off of each wing. And they basically escorted him down, and of course then he was met by the Secret Service Yeah. You know.
And he was probed.
Okay. All right. All right.
So basically, the higher the velocity, the more compressed the frequency in front of the object is.
Yeah.
Just going.
Just making sure I had that definition written down.
Is this the same kind of concept why like live sound things sound differently in different areas of the like venue? Kind of like, because different, like, the sound, it travels differently, different parts of venues. So like when you're in different areas, it sounds different. So the engineer has to walk around and listen to the sound in different parts to make sure it sounds equally the same.
Right. So part has to do with the design of the auditorium and how things are being reflected and so on.
Yeah, I thought that was more early reflection.
Is that what that is?
Right, yeah. So it has to do with that.
That's what that-
That's where you get in
Just
terms
curious
of
if that anything to do.
where do you put your speakers and all
Yeah.
that sort of thing, and what kind of materials are you using. Yeah. Right? All right. So in terms of Doppler effect, okay? After all, you think in terms of the early days, and in terms of Chuck Yeager and all those guys and fighter pilots and the whole big rush about trying to break the sound barrier and the number of pilots that they lost in terms of that. And actually when Chuck Yeager broke the sound barrier, they actually thought at the moment that they actually had lost another pilot. Because after all, they heard the big boom. Okay. But in terms of Doppler effect then, you've got, again, this can happen either two ways. It could be that the source is moving relative to the stationary person, or it could be that the source is stationary, but you're moving. So it could happen either way. Yeah, of course, a more common occurrence is that you're stationary and the object is moving, right? But if I had a speaker there, and it was just stationary, and I was going 20 miles an hour, 30 miles an hour towards it, okay? Well then, as I'm going towards it, those waves are being compressed, okay? And once I pass it, those waves are then going to be able to spread out, okay? So it could happen either way. Generally, the more common way is that the source is moving in your station, as far as the common everyday occurrence. But it could happen in either way, right? Well, in terms of this then, so Doppler effect is then, so it's going to be the apparent change in frequency due to the motion of the sound source. Okay?
Is that also dependent on the frequencies around it as well? Like say if a siren on a empty street was traveling 30 miles an hour down an empty street, would the change in frequency be different from, say, if it was traveling on the freeway at 30 miles an hour around more noise?
There's like parked cars or cars.
I think more interference with the relay may not have to pick up as much, but okay.
That's like the interference.
Right. Yeah.
Or
There'd be
destructive
other
interference
competing
kind of-
noises. Again, you get into the superposition, you still be able to hear it, right?
Yeah.
Okay. All right. All right. So, in terms of this, then there is a set of equations that deal with this, and so f prime is going to be given by f sub s
B plus B divided by.
that multiply?
Uh-huh.
Okay.
Well, V plus.
No, I mean like Fs multiplied by.
By that, yes. All right? Yes. Okay. All right. So that's the general form. And so let's go into what happens in terms of this form when the object is coming towards you or when it is going away from you. Okay? So if the object is coming towards you, okay? So if the object is coming towards you, F prime is going to be F sub S, which is the frequency of the source. So in this, so F prime will be the apparent frequency. F sub S will be the frequency of the source. V will be the velocity of sound, and then V sub S will be the velocity of the source. Okay. 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 So, for example, yes.
So what's that first equation for when the sound is going away from you?
And we'll get to that.
Oh.
Yeah.
Wait, so
Yeah. Yes. Yeah, barely depending on, and again, the other one, I'm going to rewrite that one again. Okay?
So,
Okay? Yes. All right? All right. Yeah, that's just a general way, and then later on in the chapter they give you both ways. So let's do this. All right. So let's say, for example, that my source, F sub S, is going to be 500 hertz. V, my speed of sound, will take to be 344 meters per second. And my velocity of the source is going to be, oh, let's do 30 meters per second. And the question is what is the apparent frequency given this, right? So the apparent frequency, F prime, is going to be 500 344 over 344 minus the 30. Of course, in this case, the bottom part, if it makes it easier to plug into the toy, doing the bottom subtraction is fairly simple.
Pretty simple.
Okay? So it may make it easier in terms of plugging it in if you do that.
Okay.
547.77.
So let's go with 548. We'll just round up, right? So you should end up that in this case,
Wait, let me write that.
we end up at basically 548 hertz. Okay?
Okay.
Right? Okay. All right. Now, what happens after it's gone by you? Okay? So after it's gone by you, we now will have this one, okay? So after it has gone by, we end up with f prime is going to be f v over v plus v.
Did you say it's called F prime?
Yeah. Secondary f. So again, everything means the same thing, all right? So let's again use the same information. We said that f sub s was 500, v was 344, v sub s was 30. And now the question is what is the frequency now that you're here?
So is that the same equation that you originally?
Yeah.
Yes, it's flipped around.
Right. Yes, again, it has to do with are the velocities additive or subtractive, basically.
Okay. Oh, that makes, yeah.
Yeah, okay? Okay, that's what it deals with, right? Okay? So f prime is going to be 500, 344 over 344 plus 30, and again, fairly easy to add those two numbers up to get together when you make it easier to plug in the toy.
45.45454545.
45.
That's what it says. Oh, no, I see.
500.
Okay, well, it really changed a lot.
I swear to God, I pressed 4 twice. I swear to God.
I was wondering what that.
It's going to change, but not.
500 rounded
Not
up.
quite that much.
500 rounded up, right?
Okay, 459.8.
Yeah.
So 460 to the nearest whole number?
Yes.
All right. Okay, all right.
I'm tired of looking dumb.
Again, you gotta make sure you plug it in right. Don't miss the 0. Instead of 500, you typed in 50, right?
Oh no, I pressed 344, but it only calculated 34 divided by,
that was good. All right.
So, yeah.
All right. So dot effect. And again, you can expect that next week. After all, next week, guess what? There will be a test. There will be a question like this on next week's test.
So when do we use the equation that has the v plus v0 on top of the division part of it? Because that's what you first wrote down.
Okay. First wrote down.
Awesome.
Right.
Awesome.
Yeah, so really, that's a general equation. This is the one you're going to use because this one deals with the fact that is the source movement. Okay. The other one is the general format of it, and then depending on which movie depends on which way you write it. Okay. And this one is again. This is the more. I know this is the more likely scenario, right? That the source is moving.
Yeah.
Right. Not the observer.
The other one's saying that the.
Barely the other one would be the observer's moving, which is not, really not going to happen, right?
Unless you've ever driven by a block.
All right. Other properties of waves. Other properties of waves. Reflection. Right? Let's see, everybody probably made use of that property this morning at some point in time. Everybody probably looked in the mirror to make sure they weren't going to scare people when you went out in public. Reflection. Okay? So really in terms of reflection and what happens, let's say here's my surface. I have a wave, whatever it is, if it's light, if it's sound. either one, it's the same way. The wave is going to hit the surface, and then it's going to bounce off. Right? It reflects, right? And what happens then, you got the incident angle, theta I, and then I get the reflected angle, and in reflection you get that whatever angle it comes in at is going to equal the angle
The reciprocal? Well, I guess that's
Wait,
not reciprocal, but.
what's that thing?
Yeah, what's the
Theta.
middle one?
the green bar.
Yeah,
No,
That's
no.
my normal.
It's
Oh.
the thing.
This
Yeah.
that's theta.
theta
Okay, but the little thing below.
I incident. Incident angle R is reflected angle.
Reflected angle?
Yeah. So if it comes in at 20, it bounces off at 20. Comes in at 32, it bounces off at 32. Okay? Okay. So back a number of years ago when they were working on the pier for the Victoria Clipper, and they have one of those big pile drivers out there, slamming the thing into the ground, you could actually hear the sound bounce off the Edgewood Hotel, that solid wall there.
Edgewater.
Yeah, yeah, could hear it bounce off that wall. They were doing that. Okay. So happens with light, it happens with sound. Okay. And then you think about, sometimes you go to those public restrooms, and instead of having a nice glass mirror up there, they put a steel plate up there. And how do you look in one of those?
Graffiti.
Pretty bad, right? And the thing is, what happens, the difference is that in a glass mirror, that surface is nice and smooth, right? In a steel plate, however, that surface is rough. And again, because this is always true, but the light is coming in and bouncing off at all different angles because the surface is very rough. So reflection. Right? So I think in terms of sound, reflects off of it, right? The other property then is refraction. The common example that you all have seen before is you take a glass of water, you put a pencil in it, and you then look at it. What do you see?
It's distorted, it's bent, it's
Okay? So if you take the glass, right?
Yeah.
You take a glass, you put some water in it, right? You then put in the pencil, you end up getting something that looks like that, right? When you look through the glass, right? You get that effect, right? So why does that happen?
Well, the water is magnifying the pencil so it looks bigger.
So the reason that happens
I guess I'm wrong.
is that the wave is traveling
You're against it off it.
at different velocities.
What kind of effect are you trying to get at? Is the picture bigger when it's in the water?
No, it
or
looks
is
broken.
It looks broken?
Yeah.
Oh, okay.
Try it when you get home.
Hey,
Good
John.
glass.
John, take your pencil and put it in that bottle.
Okay.
Sorry, I couldn't read it.
All right. But really what's happening here is that the wave is traveling at different velocities. So if you think in terms about the glass and the pencil and the water, is that the light is traveling faster in air than it is in the water. And that's why you're getting that effect.
So how is that, can you elaborate on how that would work with sound now? Because that's a lot.
Okay, so sound. So sound reaches a barrier. Think in terms of whatever drapes, cushions on a seat, or
Okay.
whatever, right? When that sound reaches that barrier, it's going to do two things. Part's going to be reflect. Part of it is going to travel into the material, right?
So you're talking about the absorption coefficient.
Right. Okay.
Cool, thank you.
All right. So reflection, refraction. Right? Again, general properties. Right? Also, think in terms of air and air temperatures have an impact on refraction. Right? So they actually talk about in the book, where they talk about this, they talk about the story about one of the battles of the Civil War, and that because of the air temperature, that one of the generals, who was actually relatively close to where the battle was happening, had no idea what was going on. But then the other troops who were further away could hear that there was something happening because of the sound and the way it travels. Okay. Other properties of waves, diffractions. And mainly that is that waves will bend around objects to fill in open space. Right? So waves bend around objects and will fill in the open space. Right? So again, if you're outside and you're around a corner of a building and another group of people is on the other side of the street, or on the other side of the corner, and they're talking, you'd probably be able to hear that there's somebody over there talking. Right? The way you fill in space, right?
Right.
I mean, I catch everything they're saying, but you know there's somebody there. Right? Right? So it happens with sound, it happens with light. And with that, let's take a 10-minute break. Get up straight. Right. So, the other chapter for today then is chapter 4. So we have here in terms of waves on a string. So you can talk in terms of the first harmonic, second, third, fourth, so on. Okay? So in the first harmonic, the fundamental, okay, so basically 2 notes. Okay. The wavelength is given by 2L. So if this string was from here to here was half a meter, then the wavelength of the fundamental would be 1 meter, twice the length. Okay? And F is given by F1. Okay? in the second harmonic, we have 1, 2, 3 notes, okay? And then we have 2 antennas. Okay? And now the length of my wavelength is going to be given by this. Okay? So the general formula here is now it's going to be 2L over 2. Okay? So my wavelength, in general, is going to be given by 2L over N. Where N is whatever the first, the second, the third, the fourth, whatever harmonic we're talking. Okay? My frequency, F, will be given by V over, which we saw before. Okay?
I'm sorry, one more time, what was L on
The length
the
of the string.
Okay.
Okay? So L is the length of the string, and again, like if I said my string was 0.5 meter, in the first harmonic, the wavelength is 1 meter. In the second harmonic, the wavelength is 0.5 meter. Okay. Now, the other thing about this one and this is that once I know my fundamental frequency, everything else is easy. So if, for example, my fundamental frequency was 200, F2 is going to be 400. F3 will be 600. Okay? So in terms of my string, I am going to get every harmonic, okay? And they're all going to be multiples of whatever the first harmonic was. Okay. Other things in terms of a string, and also in terms of this, that S of N, and whatever frequency, N is whatever one we're talking about, again, in terms of harmonics, will be given by N. So this deals with in terms of a string.
Could you please go back to that last screen for just 1 second?
Just 1 second. All right.
How do you find the velocity in this situation?
Well, velocity we're going to take to be the speed of sound, which will be in air,
Okay.
room temperature, basically 344, 340 meters per second. Okay. All right. All right, so T is, again, like we saw before, T is tension. Mu, we saw before. And again, we said from before that mu was basically the mass per unit length, if you remember from before. And so we said mu is given by rho pi r squared. And generally we think in terms of a string the cross-sectional area is going to be a circle. Okay? Guitar strings. Yes.
What was N?
N is
Notes.
1, 2, 3, 4, first harmonic, second harmonic.
Just any number.
Right.
Okay.
Integer, right?
Integer. Excellent. Thank you.
It's the amount of waveforms you have, right? Isn't it basically?
Huh?
Is it the amount of waveforms that you
Yeah.
have, essentially?
Well, really, it's a frequency number, harmonic number, is what N is. Okay? So N is going to be the harmonic number. First harmonic, second harmonic, third harmonic, so on. Okay?
What's T?
Tension, which we had, again, we saw T earlier, right? So again, you think in terms of a guitar string, right? After all, it's clamped at both ends. So in that guitar string, there is a certain amount of tension in that wire. Okay? So that's what that would be. L is the length of the string, whatever that might be. Again, rho is the density. R is the radius. Okay? Okay. So if you think in terms of a steel guitar string, let's say it is L is 60 centimeters. Rho is 7,700. We saw that earlier. Kilograms per meter cubed. Let's say that R is going to be 4 millimeters. Or no, meters. What's a good number for this? Okay. And what else are we going to need? T. And the tension in the string is going to be 120 newtons. Okay. So let's say I want to know in terms of what is the frequency of the first 3 harmonics. Well, basically all I need to do is calculate the value for the first harmonic, and then everything else is easy. Okay. So I got F sub 1 is going to be 1 over 60 centimeters. First off, that's not in the right units. 60 centimeters is how many meters?
0.06.
So 0.6, right?
0.6.
Right? Move it over 2 places. So this will be 0.6. Okay. T, 120, that's okay. Rho, 7,700, that's okay. Pi is pi. R is 4 millimeters. That's not okay.
No. Move it over 3 decimal places.
And we end up with
0.5.
0.004. And now we're okay. So now we take that number, plug that in. And now the fun part is, can you plug that into the toy? And get the right answer.
So this is dealing with just the first harmonic.
Right, once I know the first, everything else is easy.
Okay.
And that should be 0.04, and I forgot my square down here. Get that in there. Okay.
You just added the square there, right?
Yeah, it's pi r
The
squared.
equation, can you go up a little bit on the video, because I can't see that.
Okay.
Next to the U,
Yeah.
are
Okay.
we not doing that equation?
We are doing that.
Okay.
It's 7.36.
Mu is
P.
Okay, gotcha, cool.
Okay? Mu is rho pi r squared. Yeah, just
Okay.
did. Okay? So yeah, that .004 number should be squared. Okay? So, to the nearest whole number, we end up at
15.
15 is correct. You end up, fundamental is going to be 15. And like I said, once I know the first one, everything else is easy. Okay? So the second harmonic will be what? 30. Third harmonic will be 45. Okay? So again, once we get the first, everything else is just multiples of it. Okay? All right? So you got in terms of strings. I think in terms of whoever's got the string instruments in our group, so you got part of that stuff for strings, right? Right. The other thing the chapter talks about, besides strings, it also talks in terms of pipes. So open and closed pipes. So we have an open pipe, is rather that, it is a pipe that is open on both ends. A closed pipe is a pipe that is closed on one end. Right? And then there is some fundamental differences between the two and what you get out of it. So in an open pipe, here, in this pipe, we can get all harmonics. First, second, third, fourth, so on. Is present. In a closed pipe, you only end up with the odd harmonics. So first, third.
Is that because it's canceling every other time?
Well, because the only way it works in terms of the sound coming out is I have to end on an anti-note.
Now, is that with both, like, completely closed, or?
No, one no. You think
Just
I
one.
Yeah.
One.
Really close, there's no sound coming out, right?
No, not.
But again, if you think in terms of instruments.
Okay.
Again, you think in terms of instruments, and for those of you who got those type of instruments, you got, is it an open pipe or is it a closed pipe? So you think in terms of those who got the brass and the woodwinds. So in terms of those two types of pipes, and then you think in terms of the other example, in terms of the pipe organs. So we have in terms of open and closed pipe. Okay, so here we got, this side is my open pipe, this side is my closed pipe. Again, so here I have the relationship between the wavelength and the length of the pipe. And then in terms of the frequency. And I have the same thing going on over here in terms of the odd.
Stroking is a little fingers to excite. Two very inappropriate words to have it.
Okay, here we go. That's what I did.
Thanks, guys.
Do you have any others?
No. All right.
You have the second one.
Are you going to make these available on eCompanion?
Yes.
Okay. I'd love to print some of these out.
Yeah, probably. I'm trying to figure out how to copy this and get it into my notebook.
Right.
Not the A's. I'll have to do it differently. But yeah, I will get it there. May end up showing under doc sharing the figures for today. Just because this isn't working as far as what I wanted to do. To get it onto my printing machine. All right. All right. Hey.
Excuse me. No, it's okay. I'll go for it.
I was up pretty late last night.
Oh, you look dead.
You know, so I was watching
Other things it talks about in terms of this chapter is Helmholtz resonator, which we mentioned last week, 2 weeks ago. Again, the example being the beer bottle type thing, you throw across the opening. You get in terms of various frequencies involved. And again, it's dependent upon the opening of the neck, the volume of the resonator. Again, anything in terms of the beer bottle, the frequency of that resonator will change as you are drinking. Because as you drink, the volume of the resonator is increasing. That will have an impact on the noise. Okay. So you get in terms of this whole chapter deals with the whole topic of resonance and what resonance is. So you get this fine commercial put up by Bud Light.
Looked into this? Don't worry. I got enough for both of us. Exceptionally smooth Bud Light. Always worth it. For some of the upper boys.
Alright. So you got in terms of that. A play off on that, whole idea about the opera singer, they hit the right note and you can break the crystal glass, right? And so you have Bud Light to do take off on that for this commercial in terms of breaking it. In this case, now you know that if you do go to the opera, bring cans of beer with you. Don't bring bottles of beer with you, right? Okay? But you get in terms of residence. Right? Right? And what happens, right? So basically this occurs when the frequency of the driving force matches a naturally occurring frequency of the medium. Right? So again, the whole idea is